Okay, so we're recording the meeting. We've got Tuesday the 14th, and we're continuing in Chapter 9. We're doing physics in non-inertial reference frames. And let's take a second to remind ourselves what we did earlier in the chapter. This was a couple of days ago, and you see what we have here. We have two reference frames. We have the S0 frame with these two axes, X0 and Y0. And at that time, we were interested in relative acceleration. So the S frame was accelerating relative to the S0 frame, the inertial frame. And we had our capital A for the acceleration. Okay, we emphasized that there was no rotation. Okay, now what we're going to do in today's lecture and for the rest of the chapter is consider rotational motion. We'll keep the same notation here. Remember the R0 as a function of time. That would be the position of the particle in the S0 frame. So you would have X0 as a function of time and Y0 as a function of time, etc. Okay, and R as a function of time down here, position in the S frame. So we'll continue to use this notation, right? And remember, the lowercase r now plays a special role in Chapter 9. In Chapter 8, it was a different special role. Remember, in Chapter 8, it was a relative vector displacement between the position of particle 1 and position of particle 2. Okay, but this is our special role. So here we go. We're going to essentially draw the same picture. Now, this is going to be a little confusing because the axes will be tilted, etc. Here we go. And one of the wonderful things here is we can use these nice colorful pens. I do have the book. As you know, I'm very happy that I went to campus. I got my special permission, one-time access, and I got this wonderful book from campus yesterday. The thing is printed in black and white. So let's just take a moment to be appreciative that we have these nice colorful pictures we can draw. Okay, X0. Okay, so once again, those are the coordinate axes for the S0 frame. That's the inertial frame. Okay, and now what we're going to do here, we could consider the most general case where you have both translations and rotation, but we're going to assume that the two frames share the same origin. So this makes our life easier. Again, we'll have the capital cursive O. Capital cursive O is for origin as a point in space. Of course, the coordinates are 0, 0, 0. Okay, let's draw the coordinate axes for the S frame. Okay, so you see what we have here. Maybe I'm trying to repair this, make it a little bit better. Now, not only do I need to fix that, I really should fix the red one too. This is supposed to be nice and vertical. Come into the origin like that. Okay, so the two reference frames share the same origin. Yep, using the two colors is really the right way to go here. And so, of course, I should use black ink as I write S equals the non-inertial frame. So now it's a rotating frame. Okay. So again, for this discussion, we're assuming the two frames have the same origin and we have some sort of rotation. For the discussion we did earlier in the chapter, for this discussion, we assume the axes have the same directions, but there is a displacement between the origins. So again, the x-naught axis was parallel to the x-axis, et cetera, for the other axes, but we had this displacement. So that's a way to compare and contrast these two discussions. All right. Now, remember, when you draw these things on paper, you necessarily lose some of the clarity. I wish we had a nice three-dimensional model, and absolutely in room 72, LeConte, in the physics building, we have these nice aluminum mutually orthogonal axes with nice centimeter markings on them. And that's a nice way to illustrate that the three red axes are mutually orthogonal. It's a standard right-handed coordinate system. We're going to have to be careful with the right-hand rule. So x naught, y naught, and z naught. That's a coordinate system. And again, those three axes are assumed to be mutually perpendicular. The same is true for the black axes, right? We've got the x-axis, the y-axis, and the z-axis, and those are all perpendicular to each other, okay, as is standard for a coordinate system. So the remaining freedom now is you can rotate the three axes from the S frame here shown in black ink, and we're going to use omega, and it's going to be a capital omega, and I'm going to draw this in pencil, which will be somewhat gray in color. Yep, very nice color that emerges when you carefully shade it like that. This is the capital, right? Here's a capital omega. And that's in keeping with our notational conventions, right? We used a capital A. When, in the previous discussion, we had our capital A. Right, here's the capital A. Capital A was for the acceleration, the relative acceleration, right? The acceleration of the S frame relative to the S naught frame. Now omega, of course, this is angular velocity. Right? Angular velocity. Okay, it's the angular velocity vector, and that's the remarkable thing. In the previous discussion with remember we would think of railroad boxcars. So this was our discussion. If you had a capital V that was a constant, then it turns out both of these frames are inertial, right? We know very well that if you have a laboratory frame and then another frame moving relative to the frame, to the lamp frame with a constant velocity, they're both inertial frames. Remarkably, not true when you have rotational. The fact that this is an angular velocity means that you do have a non-inertial frame. The black frame, the rotating frame, is a non-inertial frame, even if the angular velocity is a constant. And for much of what we're going to do, we're going to assume that this angular velocity, the capital omega, that it's a constant. So that's one of the striking differences between the case of the linear acceleration and now we're doing the rotational motion. Okay, remember what we did last time? We took Newton's second law, and in this red frame here, we have good old Newton's second law. All right, Newton's second law, the mass times the acceleration on the left, equaling that capital F, that's the vector sum of all the real forces. That's precisely what we did here. Remember, we had our Newton's second law. Again, F denoting the vector sum of all the real forces, perhaps a gravitational force, electrical force, etc. All those real forces. Then we transform the differential equation. Okay, let's talk about this. There are some technical details here, but let's appreciate the takeaway message. For the previous discussion, we did a transformation of the differential equation, right? This is a differential equation that governs the motion, right? In general, this F is a function of your position. We've suppressed that here by just simply calling it F. But in general, this is a difficult differential equation. So what do? We have this big arrow indicating some effort is required to do this, we're going to transform the differential equation. Okay, so again, some effort is required to do this, but let's appreciate kind of the high level logic. This is a statement in the S naught frame, in the inertial frame, that your mass, the mass of the particle times the acceleration, is equal to the vector sum of all the real forces acting on it. So we're going to transform it, and we get a remarkable result. Assuming omega is a constant, we get this remarkable result. We have the mass times the acceleration in the S frame, that's the rotating frame. Okay, so this is the remarkable result. Let's fill in some of these details here. Okay, let me emphasize, this is assuming that this capital omega is a constant. Let's really emphasize that here. Assuming the capital omega vector, okay, so we're assuming that that capital omega vector is a constant. A nice example is if you have a playground and often there's a merry-go-round, okay, and there's a vertical axis. The axis of rotation points vertically, and if you get this merry-go-round spinning at a steady rate, sometimes we speak in terms of RPM, right, revolutions per minute. Obviously in physics we prefer radians per second. That's our favorite unit for angular velocity. So if that's a constant, then you have achieved this statement here. You have two reference frames. In that case, the black axes, what I've shown here in black, the rotating frame, you could actually paint these onto the merry-go-round right there, going with the merry-go-round. And the red axis, the inertial frame, this you could paint on the playground around the merry-go-round. And for this example with the merry-go-round, all three of these would be vertical, right? The z-naught axis would be vertical, the z-axis and the omega would be vertical. We have the usual right-hand rule. You take your right hand, you point the thumb of your right hand vertically, and then your fingers curl around in the sense of rotation. All right, so if you have an omega vector pointing straight up like so, it indicates that viewed from above, it's counterclockwise rotation. So those are our standard conventions for the angular velocity vector. Right? There's some arbitrariness, right? Certainly the magnitude of the angular velocity vector gives you the magnitude of the rate of rotation in radians per second. All right, those are the units we like to use. But it requires a right-hand rule to remove this ambiguity. We're going to choose one of the two directions. Obviously, the axis of rotation gives you this line, which we could draw in space. But now there's an ambiguity, and the right-hand rule resolves an ambiguity that we arbitrarily choose an omega vector pointing like so to indicate counterclockwise rotation as viewed if you view back looking towards the origin from this direction. Okay, so that's the standard right-hand rule for angular velocities, which you're familiar with from the 7 sequence and or the 5 sequence. Okay, having said that, let's observe we now have two inertial forces. Two, and they're very distinct. Two okay, they are distinct. We're going to talk about these both in detail. The Coriolis force depends on the velocity of the particle. The centrifugal force is independent of the velocity, so they're certainly distinct. Okay, let's take a second to compare what happened earlier in the chapter. We transformed the differential equation, and we got our inertial force, and it was just minus m times capital A. So the situation was simpler. Earlier, towards the beginning of chapter 9, we did this transformation. again, we were rewarded. We certainly have something similar to Newton's second law in the non-inertial frame. Mass times acceleration equaling the total vector sum of all the real forces. And then we had this inertial force, also called a fictitious force, minus m times a. That was the case for the railroad boxcar. Now we have the merry-go-round, or even more generally, perhaps someday you'll be on a spaceship and the spaceship will be tumbling. And, you know, famous astronaut Neil Armstrong, earlier in his career before the Apollo missions, there was a point he was in a space capsule and there was a malfunction of one of the thrusters and the capsule started spinning faster and faster. And when they spin that quickly, there's a danger of losing consciousness. That's how quickly. Okay, so a very large magnitude for this omega vector becoming life-threatening. But he was able to devise a scheme to use some other thrusters to reduce the magnitude of this angular velocity vector and thereby saving the day. So that's a real amazing story from human spaceflight. Okay, so we have these two inertial forces. Let's write down the formulas just so we have some nice clear formulas. Right, by that I mean this was a rather abstract discussion. Let's actually write down the formula. The Coriolis force, that's 2m. This is the velocity of the particle in the non-inertial frame. Okay, so that's good. Here we have the acceleration in the non-inertial frame. Here's the velocity in the non-inertial frame, cross omega. So it's a wonderful thing. This Coriolis force really is wonderful. It does involve a cross product. Okay, so that's the Coriolis. Okay, and the centrifugal. Okay, there are several ways to write this. First, we have a wonderful vector triple product. Okay, centrifugal force, not to be confused with centripetal force. Remember the distinction, centrifugal, and I advise you to remember it like this. Centrifugal is center fleeing, it points away from the center. We're going to see that here. This is a fictitious force that points away from the center. The centripetal force is a real force. You must provide a centripetal force if you want a particle to go around in a circle. There must be an applied force, and that real force, perhaps is gravitational, for example. There's a real force pointing towards the center. So the centripetal force points towards the center, center pointing, and this is center fleeing, centrifugal. All right, see how I emphasize the F in centrifugal. Okay. So let's work through this for the case of the merry-go-round. Okay, for the case of the merry-go-round, remember, it's a picture similar to this, but the omega vector is actually pointing straight up, and the z-axis is also pointing straight up. All three of these are perfectly aligned and they're pointing straight up. Okay, so again, that's the case of a merry-go-round. It's spinning counterclockwise as viewed from above. If you're a little birdie sitting up in a tree, looking down at the merry-go-round, you see it go counterclockwise. That's the picture here. All right, so let's take an arbitrary location here. All right, suppose you're sitting somewhere in the XY plane. Remember, the XY plane belongs to the rotating frame. Suppose you're sitting somewhere. We must compute, let's say you're sitting right here on the y-axis for concreteness. We must compute omega cross r. So that's this omega vector cross your position vector. Remember, r is your position vector. It's a vector from the origin to your location. So omega cross r is pointing back into the page. So far, so good. Now, that, you see it's in parentheses. That's in parentheses here. So we must first compute that. If it's in parentheses, you compute that first. It's pointing back into the page in this example. Now that vector crossed into omega is pointing to the right. Again, it's a right-hand rule. The vector was pointing back into the page. You orient your hand so you can swing your fingers up to the capital omega vector. The force, if you're located right here, what we've seen is the centrifugal force is pointing away from the center. Just as I promised you, it is a center fleeing force. A funny way to say it, it points away from the center. Okay, the Coriolis force is velocity dependent. So if you have a motionless particle sitting somewhere here, the Coriolis force is 0. Okay, we welcome that. Always nice when something simplifies for us. All right, so again, the question is, where do these two terms come from? Some effort is required to prove that these are the formulas, okay? We're gonna do that a little bit later in the week. First, we'll explore the wonderful world of the Coriolis force and the centrifugal force, and then we will return to go through the details of the derivation. Okay. And one reason we're approaching it this way is the next homework assignment is due Friday, right? So it was posted 4 days in advance and it's due Friday. And that homework assignment will involve quite a bit of work with the Coriolis and centrifugal forces. Okay, so in Taylor's book, there's something that is called the useful relation. Okay, there's no fancier term than that, but if you look at the chapter 9 summary, and see now that I have the book printed on paper here, it's so easy for me just to leaf around in this. I just love it. A good old book printed on paper. Yeah, it's called the quote useful relation. It's right there in the chapter summary, the useful relation. And let's use the same terminology here. So what does this useful relation do? Well, it really is just an embodiment of the definition of what an angular velocity vector is, together with some vector calculations that give you a very powerful result. And that very powerful result okay, so this is our useful relation. We'll be using this constantly throughout the chapter. Notice we have a lowercase omega. So the idea is the useful relation can be used in a variety of contexts. The typical lowercase omega, right? You know, the lowercase omega is more common. Typically, when we talk about the motion of an object, we talk about its velocity. And if it's a rigid object, so more complicated than just a point particle, if it's some sort of rigid object, then in addition to having a velocity, a center of mass velocity, it also has some sort of instantaneous angular velocity. We like to use little omega for the instantaneous angular velocity of an object. So it could be a space capsule, for example, or a satellite, maybe some communication satellite. So we're thinking of a rigid object. At any instant, there's this lowercase omega, which tells us about the state of rotation. It tells us about the axis of rotation. Right? Since it's a vector, it uniquely identifies an axis in a three-dimensional space. And again, the magnitude together with the right-hand rule tell you the rate of rotation about that axis. So let's take a second to unite this discussion with our earlier discussion. We're using the capital omega, right? There's a capital Greek omega there to describe the rate of rotation, the relative rotational motion of the S frame relative to the S naught frame. And so we'll talk about how this useful relation V equals omega cross R, how it relates to this discussion here with the capital omega, right? Certainly there will be a direct transcription of the formula. And that direct transcription is to say, if you have some particle, say it's motionless in the S frame, just for simplicity, some fixed particle in the S frame, what's the velocity in the original laboratory frame? Again, we must do a cross product. So again, we will take this formula and incorporate it into our discussion with the two reference frames. But the formula is actually more general, right? So you can discuss this formula before launching this big discussion of two reference frames, one of them inertial and one of them a non-inertial frame rotating relative to the inertial frame. So this is intended to be a quite general discussion. Let's draw a picture to go along with this. So again, it's a wonderful formula. Notice we don't need any sines and cosines. It's simply a cross product. All right, let's appreciate how this picture emerges. Okay, so without loss of generality, we're going to have this omega vector pointing vertically upwards. Okay, and a nice way to visualize this, suppose you have a block of styrofoam. It's a nice big rigid block, and it's something you can easily spin around and do some thought experiments. Okay, and what we're doing here is we've chosen the omega axis to point vertically upwards. That means we're going to take this block of styrofoam, it's a rigid object, and we're going to rotate it about a vertical axis. Someone looking down from above would say it's rotating counterclockwise. That is what we have communicated here in this picture by drawing this little lowercase omega vector pointing straight up. Okay, so for any point in the block of styrofoam, all right, so again, here's an origin. So there's the origin, okay? That is a point in the block of styrofoam that's motionless, right? And it remains motionless, okay? The same is true for all of the points that are here on this axis. All of the points on the axis of rotation are motionless, okay? So let's consider a typical kind of generic point. Okay, a generic point in the block of styrofoam. And notice for the useful relation, we're using just the R vector for the ultimate simplicity in notation. So what I'll do is I'll draw kind of a horizontal line here to indicate that this discussion we're having here of the useful relation, it's actually a very general discussion. It's logically distinct from our earlier discussion in this lecture with the two reference frames. Okay, this is a very general discussion about angular velocity vectors. And if we follow through the logic carefully of what it means to be an angular velocity vector, we're going to see that the velocity vector of this point in the styrofoam is given by omega cross r. Okay, wonderful result. And again, the diagram we're going to draw, it could include some trigonometric functions. So it's really nice that this result, as you know, a cross product in Cartesian coordinates is just a handful of a few, maybe 6 multiplications and some subtractions, stuff like that. Okay, so if you have this point here, now we're going to draw a perspective diagram. The tip of this arrow is going to move around a circular path. And if we agree that this diagram is a perspective view, okay, so this diagram is a perspective view. Okay, what does that mean? It's not an edge-on view. This circular path lies in a plane that is perpendicular to the omega vector. So if this were a side view, this circular path would appear as a line segment, a horizontal line segment. This is a perspective view. Again, the circular path lies in a plane that's perpendicular to the omega vector. Okay. What's the radius of that circle? Well, we like to use rho, lowercase rho. Okay, there's a pretty small lowercase rho. That's the radius of the circle. And yeah, there's some trigonometry involved. If this is a theta, if this angle is theta, we typically do use that angle theta for the angle of the r vector relative to the z-axis. No doubt about it. Rho is equal to the length of the r vector times the sine of theta. Okay, so again, this is the geometrical picture. If this omega vector is constant, then the tip of the r vector executes uniform circular motion. It's moving along a circular path with a constant speed. Okay. Now, by the very definition of angular velocity in radians per second, we see that the speed, remember the speed is the length of the velocity vector, so that's simply the symbol v. Okay, so what have we done here? We've used our knowledge of angular velocity. If it's measured in radians per second, then the angular velocity tells you, if you multiply by time, it gives you the angle measured in radians, and the distance traveled, because of the definition of radian, is that angle measured in radian, which would be omega times some time interval. So you're measuring the path, the arc length along this circular arc. Another way to say it is the circumference of this circular path is 2 pi rho, right? And the period is 2 pi over omega. So those are equivalent ways to think about it. But the upshot is that the speed, right? So we're having two separate discussions here. This one involves scalars. We don't have to worry about vectors here. So this speed, v, is rho times omega. And that's a statement about scalars. The right-hand rule, which obviously is present here. If you have a cross product, we certainly have a right-hand rule. The right-hand rule will give us the direction. So the velocity vector, and again, drawing this on paper is challenging, but I must emphasize that this velocity vector is tangent to that circular path, and the circular path is shown here in perspective. It looks like an ellipse, but it's a perspective view of a circular path. So there you have it, the instantaneous velocity vector here. This is our v with, when we write it by hand, you put the arrow on top. So that symbol, v with the arrow, that's the velocity vector. That's the velocity vector of the tip of this r, right? R is the position vector. So if you have some point in space, and we started this discussion thinking about a block of styrofoam. It's a nice way to think of a rigid object. You can easily spin it about any axis you like. Here we're going to think about, again, the case of steady rotation. So this omega vector is a constant, and you have this block of styrofoam rotating about this fixed axis in space. Okay, so these two statements now, you see we have two statements. Here on the left, we have a statement about the magnitude of the velocity vector, that's the speed. And here on the right, we have a diagram that shows us the direction. Those words we said earlier about the tangency, the fact that this velocity vector is tangent to the circular path. Okay. So that agrees exactly with our notion of the cross product. Okay. If you compute omega cross r, remember for a cross product, you take your right hand, you orient your fingers so they're pointing in the direction of the first factor. You have some freedom to rotate your hand about that direction. You must use that freedom so you can sweep your fingers to the second factor. So I got to go like this, sweep. Okay, that's the only way to do it. And then your thumb points in the direction of the cross product. So it's a nice example of the right-hand rule. So in summary, we've proven this, right? Because we know the magnitude of a cross product is omega sine theta r. Okay. And so this celebrated result, right? It really is a useful relation. As we go through homework problems, etc., on a typical homework problem, you may have to identify the context for how you're going to bring in this useful relation. But again, the crucial thing is the definition of an angular velocity vector. Okay. We've proven it by doing a separate analysis of both the magnitude here and the direction over here. So wonderful relationship. Okay, so we're going to start looking at some problems that involve the Coriolis force and the centrifugal force. Okay, and as we go through some problems, we'll gain familiarity. Then, as you know, we just love talking about power series. We talk about ordering parameters. We talk about small parameters, first order in smallness, second order in smallness. And so this powerful tool of using a power series will be a wonderful way to investigate some interesting physics. And if we ever get to go back to campus, we could actually do this right next to the physics building. We have this wonderful clock tower, the Campanile, right? Something like 94 meters tall. And yep, you can access with your student ID. You can, with my faculty ID, I get in for free. I'm sure it's the same for you. Now, while we don't have immediate access to the center of the tower, and I think they actually store some dinosaur bones in there or something like that. But imagine this, if you had access to that, to the elevator shaft, you could do an experiment where you drop a particle. So we do need this to be carefully done, and that's why we like this clock tower. Any sort of wind, right? We'll often have significant winds in that area. Any sort of wind would mess up the experiment. But with this wonderful clock tower, we would have a fully enclosed shaft. We could drop an object from rest, and there's going to be some interesting stuff going on with these forces. There will be a slight deflection, right? Obviously, the simplest analysis you could do is say, well, the particle is going to accelerate downwards with an acceleration of 9.8 meters per second squared due to the gravitational pull. But then remarkably, as it gathers speed, we got the Coriolis force. It's going to deflect it. And so what we're saying is here is the entire Earth is a rotating frame of reference. So we'll be talking about some experiments that are sensitive enough, right? Often we ignore the fact that our laboratories really are rotating. Once a day, they rotate through a full revolution relative to the so-called fixed stars. Again, that's a way of invoking a notion of an inertial frame. So we'll talk about several experiments that are sensitive enough, right? The angular velocity of the Earth spinning on its axis, that's 2 pi radians every 24 hours. You convert that to radians per second, it's a pretty small number, very, very small. And that's why the Coriolis force numerically in MK units is going to be small. And ditto for the centrifugal force. Okay, so these kind of some similar topics will be on the homework too. The notion, this is the homework that's due Friday, right? Homework 6 is due Friday. The ability to set up these problems and to do a power series expansion. Okay, now let's talk about an experiment, and this is a fun one. You know, there was a time when amateur astronomers would grind their own mirrors. You get a slab of glass, you can order a slab of glass, and then you spent a couple months in the basement grinding this, and you must grind it to sub-wavelength precision. If you're going to build a decent telescope, you have to grind this mirror to extraordinary precision. And there are ways of controlling the accuracy, right? Obviously, optical methods to verify. You need this thing accurate to sub-wavelength precision. So we'll talk about what happens if you could possibly avoid a lot of unpleasant grinding if you could do this experiment. If you take a bucket, fill it with water, and spin it about a vertical axis. If you wait for hydrostatic equilibrium in the bucket, right? So this would mean somebody in the non-inertial frame, perhaps a little bug sitting on the edge of the bucket, looking at the water and waiting for it to reach hydrostatic equilibrium. The surface of the water would become curved. Okay, and we're going to compute that. We have a nice paraboloid of revolution. That would be perfect if you could freeze it. So if you could do this experiment in some sort of large freezer, keep it spinning about a vertical axis, freeze it, and you would have a wonderful paraboloid of revolution. Okay, ideal, just put a reflective coating. Even without a reflective coating, it would still have some reflectivity, and you could start observing the stars. So let's talk about this fascinating problem here. And this will be our first, first calculations, right? We have two forces to worry about now, the Coriolis force and the centrifugal force. Well, for this experiment with a rotating bucket of water, if we're waiting for hydrostatic equilibrium, there's some great news. The water is motionless in the S frame, so the velocity is 0. Excellent. So this Coriolis force is 0. There remains the centrifugal force. Okay. So here's an example. Okay. The spinning bucket of water . Okay, so let's draw a picture again. We're thinking of a cylindrical bucket. Okay, that's supposed to be a cylindrical bucket. Imagine, as buckets often do, there's a handle. So this is the handle. Good, because we need to attach a string here. The top, remember this is a perspective view, so the top of the handle is right here. No question about it. String. Supposed to be a straight piece of string here. Okay, this is all you need to do this experiment. Just put some water in the bucket, get this thing spinning. All right, so again, this was a perspective view of our bucket. The water is in there. We have this axis of rotation. Okay, and we're gonna see that the surface of the water becomes a paraboloid of revolution. So how do we draw this? Well, drawing a paraboloid of revolution in perspective is a little bit challenging. I would encourage you to first draw the circle, which is where the water surface meets the wall of the bucket, like so. So far, so good. Okay, and now let's try and capture this idea that we have a paraboloid of revolution, maybe something like this. Yep. Very challenging, very challenging. This is a, I think that's as good as it's going to get here. A paraboloid of revolution. Okay, so let's understand what's going on here with the bucket. So the key is we're going to analyze this in the S frame. Remember, the S frame is the non-inertial frame. So imagine you're sitting there at the edge of this bucket looking down at the water. Okay, and what do you see? Well, you wait for equilibrium, hydrostatic equilibrium. Again, we'll talk about our old friend, the non-gravitational force, right? The buoyant force, which will be perpendicular to the surface. Okay, so the Coriolis force will be 0, so we have hydrostatic equilibrium. Hydrostatic equilibrium in the S frame. Okay, wonderful. So we love this because R dot is 0 and okay, and let's be clear on the notation. Remember the R vector without the little 0 at the bottom of it. The R vector is the position in the S frame. So this is the statement that the velocity in the S frame is 0 and the acceleration in the S frame is 0. Let's compare that with the S naught frame for a moment. The S naught frame is often called the laboratory frame. For an experiment like this, that would be a good choice of words. The laboratory, for example, the room that we're in, is motionless. That's the inertial frame. I haven't drawn the axes here. But in the laboratory frame, a little parcel of water is executing uniform circular motion. So the velocity is not 0, the speed is not 0, and the acceleration is not 0. So let's emphasize that here. R naught dot is not 0. Okay, so that was a parenthetical remark. You see I put parentheses around it, but just to really be clear on the notation, the remarks here in the S frame, so that's the frame spinning with the bucket. In the S frame, we have 0 velocity and 0 acceleration for all these little points. And we're going to focus our attention on one little parcel of water. There, I marked a little parcel of water. Okay, so it's important to understand that these are non-zero back in the laboratory frame. Okay, so here we go. 0 is equal to, it's supposed to be an equal sign. Okay, and this is equal to, our notation is F. Remember, F is the vector sum of all the forces that are real forces. These are the forces that you can identify in the inertial frame. Plus, now that we're in the S frame, we have the Coriolis force and the centrifugal force. I'll put a 0 to remind us the Coriolis force is 0, but we do have a centrifugal force. Okay, so there you have it. And again, the Coriolis force is 0 because the velocity is 0 in the S frame. Okay, great. So let's continue here. We have studied this decomposition intensively, right? This vector sum of all the real forces, for what we're doing here, we've got the non-gravitational force. F sub ng, that's non-gravitational force. That's the buoyancy. And then we got good old mg. That's the gravitational force. So I put parentheses here to indicate this quantity in parentheses is the capital F, which is the sum of all the real forces. Okay. And now we have a formula for the centrifugal force. It's M times the cross product. We got the omega cross R cross omega. I ran right into the diagram, but it's okay. It's still legible. Everything's cool, right? Not the best omega I've ever drawn, but okay, so this is the key to unlocking the joy here for this problem. Let's take a second to investigate this. I'll use the color here. Centrifugal force, here's the formula. Okay, it's a double cross product. No problem there. As you know, the textbook has the formula. Okay, here's inside back cover of the textbook. Can I squeeze it onto the, I got a tripod blocking my motion here, but what do we have here? A vector triple product. The back cab rule, the famous back cab rule. Okay, yes, I got special permission to do that. As you know, this is copyrighted material. Yep. The logic goes like this. The physics library has this book, and now the physics library is supposed to be accessible to UC Berkeley students. Therefore, I am justified in showing you pages of the book. We're not breaking any rules. Everything's cool. All right, so let's deal with this. We have to grapple with the vector omega cross R. Now, this is a very useful calculation. This is also examinable material. Figuring out this cross product and then another cross product, that's something you could see on an exam, right? It's a really good problem. Let's look at that for a second. Okay, so here we'll have a separate discussion here. We want to really appreciate this omega cross R. Of course, that evaluates to become a vector. You take that vector and cross it into omega. what happens. Okay, let's watch the dramatic action here unfold in front of us. This loopy arrow helps to remind us about the right-hand rule. It's a loopy arrow showing us there's an angular velocity. Okay. And the typical scenario is you have some, just as we discussed a moment ago, a typical path of a point is a circular path. The circle lies in a plane that's perpendicular to the axis of rotation, right? Just a moment ago, we went through this. We had a lot of fun with this calculation. We're invoking the same three-dimensional mental image, right? The same picture here. We have a circle. The radius of the circle is rho. Okay. And then what we discussed is that the cross product, our first cross product, remember the r vector, you could draw the origin down here somewhere, as we did a moment ago. Then you would have a very clear statement that the r vector is like so. And omega cross r is tangent. This is what we observed. Now let's really emphasize it. The result, if you compute this cross product, omega cross r, okay, it's tangent to the curve like so. Now that is true for the picture we drew earlier today. We had the r vector as indicated by my pen. And again, you can go through the motion. Since the omega vector, let's emphasize it like so. The omega vector points straight up. You can do the cross product. You get this vector, which is tangent to the circle. So hopefully the existence of this circle, the knowledge that it lies in a plane perpendicular to the z-axis, helps to conjure up a mental image here that this vector is tangent to that plane, and therefore this vector lies in that plane that's perpendicular to omega. That's true quite generally, that if you evaluate a cross product, it's perpendicular to both of the factors. All right, so let the record show we could have chosen the origin somewhere else. We could have chosen the origin here. We could have chosen the origin at the center of the circle. We could have chosen the origin up here. Suppose we had chosen the origin up there, well then the r vector would be like that. But again, the cross product is insensitive to any component of the r vector that's parallel to this axis of rotation. So for all of these cases, for any choice of an origin on this axis, the result for omega cross r is the same, and it's this vector that's tangent to the curve. Okay, now let's take it up a notch here. I'm going to draw a radial extension. Remember, we identified rho. Rho, in harmony with our deepest thoughts and feelings about cylindrical coordinates, rho is measured, and it's a distance from the axis of symmetry, and it's measured directly out. And this line segment in a three-dimensional space, this line segment is perpendicular. So the usual notation there is you draw one of these angle markers. Again, it's a perspective view, so this line segment does not look, drawn on the paper, this line segment is not perpendicular to this axis, but in a three-dimensional space, this line segment is perpendicular to the axis. And let's draw the extension. Okay, so that's the radial extension. The direction, of course, is the rho hat, right? We love cylindrical coordinates. This direction is the rho hat direction, okay? So omega cross r points in this direction. I'm going to also diagram you see what's emerging here. This vector pointing radially away from the axis, this is the omega cross r cross omega. Okay, now these two vectors have different units. There's no way to say that one is longer than the other because they have different units. You cannot compare the lengths of two vectors that have different units. This omega cross r has units of meters per second. and this one has units of meters per second squared. So there's no meaningful comparison. You see, I drew this one a little bit bigger. You could draw it smaller, you could draw it with the same length, it doesn't matter. The purpose in this diagram is only to show the direction, but there's no meaningful comparison between the two lengths. So it was arbitrary for me to draw this one a little bit longer. Okay, and again, the direction is radially outwards. You prove that by computing the cross product. So you take your right hand, you point in the direction of the first factor, that's omega cross r. You have some freedom to rotate your hand. So you choose it so you can rotate into the second factor, and then your thumb points radially outwards. Okay, so again, we've proven that the centrifugal force points radially away from the axis of symmetry. Okay, so you can go through this, this first factor here, the omega cross r. We can squeeze this in. It's the magnitude, and of course the magnitude is the omega r sine theta. Okay, that's pretty small sine theta, but it's visible. Phi hat. Okay, we're using cylindrical coordinates. Okay, and then when we form the cross product, the nice thing here, this second cross product is a cross product of two vectors that are already orthogonal. The vector inside the parentheses here, that was the result of the first cross product. That vector is tangent to the circle. Omega points straight up. Those two vectors are orthogonal, so there's no further trigonometric factor to worry about. Okay, so the magnitude of this vector, we can just write this formula out explicitly. We get the omega squared r sine theta rho hat. And remember, r sine theta is rho. This r sine theta is rho. Okay, so it's a wonderful result. This vector triple product, the quantity omega cross r, that quantity crossed with omega again, is radially directed. It points away from the axis of rotation, and the magnitude is omega squared times your distance from the axis of rotation. Okay, so we can write that here. And let's rearrange a bit. We now have a wonderful conclusion. You remember last time it was very useful to isolate the non-gravitational force, that's the buoyant force. So I'm going to put it on the left with a minus sign. And we have this mg, okay? Let's be clear. Because g points in the minus z hat direction, we'll write that as mg z hat. Okay? So again, I'm using the conventions that g is the magnitude of the g vector. That's the best thing to do. Some people define the little g to be minus 9.8 meters per second squared. That's unfortunate because we have a very general principle that if you have the symbol of just the symbol for a vector with no arrow, that's the magnitude of the vector. So the best practice here is to have little g be 9.8 meters per second squared. Then this vector points in the minus z hat direction. So there's our formula. Okay, and then we've got this one here, plus m omega squared rho hat. Wonderful. This is very important to us. Again, this is important to us because we've isolated the non-gravitational force. This is perpendicular to the surface of the water. The non-gravitational force is perpendicular to the surface of the water. The same is true from -1 times the non-gravitational. Either way, perpendicular to the surface of the water. Okay. Now again, both of these forces can be written as gradients of a potential. Okay. So we're going to introduce a potential U equaling mgz minus a 1/2 m omega squared rho squared. And here I go again with this textbook. I just think this is the greatest thing ever. This is the inside back cover, right? We've got the gradient. There's the gradient. Here it's called cylindrical polars. That's a little unusual. Most people will call this cylindrical coordinates. There's the formula for the gradient. That's what you need here because we've written this in cylindrical coordinates. It's just a constant times rho squared. You compute the gradient with proper attention to minus signs, etc. Okay, so this must be an equipotential, right? This logic now is the same as what we did for the tides. We've identified this capital U. We know the surface of the water will be an equipotential. So surface is described by U equals constant. That is what it means to be an equipotential. If the potential is a constant, you have an equipotential surface, okay? And it is a two-dimensional surface in a three-dimensional space. Okie dokie, great. The upshot then, you solve it, you clean up a little bit, and you get Z equals Z naught plus a 1/2. We have a nice omega squared over G rho squared. Okay, there's the formula. And we said this was a paraboloid of revolution, right? Let's connect those two statements now. Paraboloid of revolution, boom. I guess that's not going to fit on the, yeah, it actually does fit. Okay. So we've proven that the surface is a paraboloid of revolution. You see this has the structure Z constant quadratic term. So Z is a constant plus a constant times a quadratic term. Okay. Paraboloid of revolution. So let's continue now with the fascinating world, the world that you live in if you're in a rotating frame of reference. There are Coriolis forces and there are centrifugal forces, okay? So let's move on to our next example. We're going to be doing some experiments where we drop an object and we do precision measurements of the motion, the subsequent motion. We're going to begin by looking at the initial acceleration. What happens in that first instant when you release an object from rest? And then later we'll have a more detailed discussion as it plummets, right? Imagine we get access, our dream is to get access to the elevator shaft inside the campanile. It's a perfect environment for doing this kind of experiment. So the first step is free fall from rest. Again, this is going to be wonderful. We love it when the velocity is 0 in the non-inertial frame. Coriolis force is 0. So that's the key word here. It's starting from rest. We can talk about the initial acceleration. Okay, so our definition now, and here's where we have to be careful. There's a distinction now between the familiar gravitational pull due to the Earth and the initial acceleration. So here's where we get to really do some precision work, so to speak. Now the notation is going to be challenging. Let's just stay very focused on the notation. We're going to define this lowercase g to be the initial acceleration if you drop something, okay, from rest. So the 3 horizontal, this is like a glorified equal sign. It indicates we're talking about the definition. This is the definition of our symbol lowercase g, initial. And let's underline, we want to emphasize, this is the initial acceleration when something's released from rest. As it gathers speed, the Coriolis force is going to confuse our lives mightily, but the initial acceleration when you have an initial velocity of 0, right, is much simpler. And it's important to understand it's relative to the Earth. Okay, let's write this. okay? That's very important relative to the Earth. And the Earth, for what we're doing now, we're going to do precision measurements. The Earth is the S frame. It's the non-inertial frame. We're going to be sensitive enough to detect the rate of rotation of the Earth about its own axis. And the Foucault pendulum, right? Many museums have Foucault pendulums. You can sit there and watch them. Amazing, and they're sensitive to the rotation of the Earth. So, okay, unless you're at the equator, life is a little different there. Anyways, for this discussion, the Earth is the non-inertial frame. So that's important to point out here. Oftentimes we talk about our laboratory. In fact, for most of the demonstration we do in the physics building, we talk about our laboratory as being an inertial frame. Here, there's a bit of a role reversal because now our laboratory is a non-inertial frame. It's slowly rotating because of the rotation of the Earth. Okay, so when we emphasize initial, so this is while V equals 0. Okay, and let's bring in some color to really emphasize this. We're releasing the particle from rest, and that's why we have this initial velocity of equals 0. Okay, now here's dangerous notation. It's dangerous, but we have to talk about this. Okay. The notation here, G naught, is minus GM Okay, so this is the gravitational field. Remember, gravitational fields are measured in meters per second squared. You take a gravitational field, you multiply by the mass of a little test particle, you get the gravitational force on that little test particle. It's just like an electric field times the charge on a particle. So this is the gravitational field due to the Earth, and we're assuming a spherical Earth here, okay? And the G naught, now we are going to use this G naught even in the non-inertial frame, so it's better to think of this simply, maybe we should have used a different letter, so we did not have to utter that little naught there, because that's going to cause some confusion. Let's just accept the fact that this G naught is shorthand for this nice collection. Now this points directly at the center of the Earth. The remarkable thing is we're going to see this G vector does not point directly at the center of the Earth. And the reason is the centrifugal force. There's a small centrifugal force because the Earth is spinning. So if you hang a plumb line straight down, that's just a fancy way of saying you have a massive, something like a chain with a, especially nice if there's a mass at the bottom. If you wait for it to equilibrate, it appears to be vertical, but it's not pointing straight down at the center of the Earth. There's a slight discrepancy. And so that's what we're going to compute here. We write down Newton's second law. Okay, there's our Newton's second law. Remember, we're talking about releasing a particle from rest, that first instant when it's still at rest. The Coriolis force is 0 because it's velocity dependent. We do have the centrifugal force. Okay, so let's write this out. Okay, and so this is the mg naught. Okay, so once again, we evaluate the cross product. This is something we discussed when we discussed the bucket. And so the upshot is we can write this wonderful result. This G, right? This initial acceleration, what we're talking about now is a very precise result for this G. G is equal to the G naught. G naught points at the center of the Earth. And here's the small correction. And it's omega squared. That's remarkable. Remember, omega, if you write it in MKS units, it's a small number, right? 2 pi radians divided by the duration of a day, something like 86,000 seconds. Now we're talking omega squared, so in MKS units, this is a very small number. Radius of the Earth, that's pretty big. Something like 6 million meters, right? Sine theta. Theta is the co-latitude. Rho hat. All right, wonderful result. It's interesting we have this competition, so to speak, between the square of omega, right? Omega is a very, in MKS units, that's a small angular velocity. R in MKS units is around 6 million meters, right? So 6 million. So you can see it's a product of a large number and a small number. The upshot then is this is a small correction. It depends on your latitude. Remember, theta is the co-latitude, 90 degrees minus the latitude. Okay. So now we're going to launch into some interesting discussions with the Coriolis force. Okay. Because of the cross product, there's some kind of counterintuitive stuff that happens. Okay. And there are interesting examples also from naval artillery. So if you think of large warships, when they fire the naval artillery, they actually have to take into account the Coriolis force, actually just deflects the projectile. Well, in the Southern Hemisphere, for example, during the Falkland Islands War, at the end of the 1900s, in the Southern Hemisphere, the Coriolis force kind of goes the other way, because when we work out these cross products, we'll see, we're going to go through some examples. So the upshot is they were accustomed to having certain corrections due to the Coriolis force. Well, in the Southern Hemisphere, the corrections were backwards, and that was actually, it would be like tens of meters, the discrepancy between the two formulas. Okay, so let's talk about the Coriolis force. We're going to start getting some familiarity with the Coriolis force. Okay. Once we get this familiarity with the Coriolis force, then we're going to revisit this experiment. If you take a particle and drop it from rest, in some sense, one of the simplest experiments you could do, dropping a particle from rest in a controlled environment, right? So obviously the wind would mess up our measurements. Must be a sheltered environment. And we're going to see how to analyze the motion as the particle gathers speed falling down the elevator shaft in the campanile. Again, that's a great way to think about it. The Coriolis force is going to deflect it away from a reference. How could you measure the deflection? Well, a hanging chain would be a wonderful reference point. So step one is you obtain a long chain, 94 meters long. You hang it down the elevator shaft and wait for it to equilibrate. When it's motionless, you have a wonderful reference, okay? Then you drop a particle, you let it fall, and you see it's going to land a couple centimeters away. It actually gets deflected. When it finally hits the bottom of the elevator shaft, it's about 2 centimeters away from the reference line. Okay, so here we go with the Coriolis force. We're going to have a 2-dimensional discussion and a 3-dimensional discussion. Okay. So for the 2-dimensional discussion, I just mentioned that because these diagrams are easier to draw. The 3-dimensional, this again, it's wonderful if you have 3-dimensional models available, it's the right way to go. Otherwise, you're forced to draw pictures. And over here, I will do my best. Look at that, pretty good circle already. I will do my best to draw the globe. Okay. Now, if you want to do a quality job here, here's the equator. Okay, because this is a perspective view. Well, then the North Pole is here. If you draw a perspective view of the Earth, then the North Pole is here. It's not up here. This is the horizon. Here's the North Pole. Okay, so this is the kind of precision we're going to be doing. And so here are the so-called parallels. Okay, and we'll talk about the typical weather systems. You know, the Coriolis Force is responsible for the fact that in the northern hemisphere and the southern hemisphere, you have the typical circulation of these weather systems that are visible in satellite imagery. Okay, so again, an appreciation of the Coriolis Force. So that's the three-dimensional picture. Here's our globe with the Earth. Here's the equator. Okay, and then the meridians go north, south. Typical meridian, such as the prime meridian, okay, so that's a meridian going from the North Pole to the South Pole. Okay, so for the two-dimensional case, think of something like a merry-go-round. Okay, now for this discussion, imagine omega is pointing out of the page. So I'm using my pen cap here. Omega is pointing out of the page. The usual convention there is to draw a little circle. If you want to draw a diagram and indicate that a vector is pointing out of the page, you typically draw a circle like so. Okay, so that's our omega pointing out of the page. Okay. If you want to draw a vector pointing into the page, you do something similar and put a cross, kind of reminiscent of the fletching on an arrow, the feathers on an arrow. So there's our omega. Let's work out some examples. Okay, so if you have this merry-go-round, and if you're a scientist with a laboratory set up on the merry-go-round, okay, suppose a particle is moving like so. Okay, so omega is coming out of the page, v is pointing like so. The cross product, if that's the velocity vector, the Coriolis force for that one is right at the center. So in 2 dimensions, you can draw this easier. It's going to be harder in 3 dimensions. Okay, let's do another one over here. So here we go. It's going to be right angles, right? So suppose the velocity is like so. Remember the Coriolis force. We talked about this earlier today. The Coriolis force, there's a multiplicative scalar, 2m, that's a scalar, right? It's positive, that's all we care about right now. Velocity crossed omega. Velocity crossed omega. Just remember, we have to figure out the velocity crossed omega. So v cross omega like so. So I'm using my right hand for the first one. That force vector like so. V cross omega here. Again, it's right at right angles, so F core. And again, the remarks we made earlier, the velocity vector and the Coriolis force, they have different units. It's not possible to say one is longer than the other. In these diagrams, we just want to show the direction. Sometimes we may draw them slightly differently, having slightly different lengths. The reason is just to kind of show that there's some different, they're not identical in length. So yeah, these are a few examples. Now let's get right to work on the situation here in this picture. We're going to imagine if you're on the surface of the Earth and you throw an object due south. Due south means directly south. Okay, so if the velocity vector is directly to the south, I've drawn the velocity vector. Turns out the Coriolis force is to the west. That's going to the west. And so if you're a famous baseball pitcher and you throw a pitch due south, there's a Coriolis force with a deflection to the left. And this is also relevant to people who fire rifles, right? Marksmanship. There's a deflection of the projectile. Okay, so there's a Coriolis force. In the southern hemisphere, it's the other way. So in the southern hemisphere, right? We're going to figure out a cross product. Okay. So again, the crucial thing is to figure out this cross product. The omega vector, can I squeeze it in there? Omega pointing straight up like so. Okay, so I see we've reached the 2 o'clock hour, so we should finish today's lecture. In our next meeting, we'll revisit this and go into more details. So I'm going to pause, actually, I'm going to stop the recording and I'll stay here to see if we have some questions. So